Okay, we're going to talk about the language of sets today. The use of the word set as a formal mathematical term was introduced by Georg Cantor in 1879. Just a little piece of trivia for you. It is a collection of elements. Okay. We use set roster notation to indicate the contents of a set for elements of a set. Say we have X with a stylized E is said to be an element of S. Likewise, X stylized E with a line through it means X is not an element of the set S. Set roster notation is where you write all the elements, all of its elements between curly braces. So, we're separating the elements with commas. For large or infinite sets, you can use the ellipsis symbol. So these are the first four even natural numbers. So all the natural even numbers would be 2, 4, 6, comma, dot, 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 to indicate that it goes on infinitely. Okay? Or if you want to just do the natural numbers between 1 and 100, rather than do them all out, you can use an ellipsis to indicate the large quantity in between the two numbers. So that's the set roster notation. The axiom of extension, that's you're still writing here on some folks here. But yeah, this is called an ellipsis. It's 2 L's, right? Yeah. But the axiom of extension says that a set is completely determined by what elements are, and not the order in which they may be listed, or the fact that some elements may be listed more than once. So, determined by the elements. So, say set A equals 1, 2, and 3, and B equals 3, 1, 2, and C equals 1, 1, 2, 3, 3, 3. All of these sets are equivalent. In mathematical terms, they are equivalent sets. Because the order doesn't matter, and duplications don't matter either by the axiom of extension. So, sets can also be nested. So, let's see here. So, that is a valid set. It has two elements. The element 1 is an element of S, and the set containing the element 2 is an element of S. The number 2 is not an element of S. See how that works? It just the set with the element S, 2 in it is an element of S. So, let's see here. So basically, the set, a set with a single element is not equivalent to its the element in there. They are not the same. A set is a set, can be manipulated in a variety of ways, and an element is an element is an element and can be manipulated in different ways. So like I said, this is last time, this is formalizing some simple concepts that we'll be using later on for more complex discussions. Now, some sets are pretty common. The set of real numbers Z is the set of all integers Q is the set of rational numbers and N, I mentioned earlier, is the set of natural numbers. Anybody know what the set of natural numbers is? One, two, three, four, etc. Doesn't start at 0. It starts at 1. So that's the natural number. Now you can add a superscript. Sorry, not a subscript. Plus or minus. So like z plus is positive integers. With a minus sign there, you could call it, it would be the negative integers. Typically, the plus or minus superscript is used with the integers rather than the other sets, although you do see it, and it is acceptable notation to use. Now, real numbers are often pictured as being all the points on a line with 0 at the origin. So you have that. But I believe from previous math classes you're familiar with these terms, though the Z, Q, N may not be familiar with those, but I don't know where they get the Z for the integers. Q is for quotient because the rational numbers are quotients, and natural numbers for N for natural numbers. But those are some commonly used sets and notation that we will be seeing quite a bit of this semester. Now you could also use set builder notation to denote a set. Say, let S be a set and let P of X be a property that elements of set S may or may not satisfy. We define a new set to be the set of all elements X in S such that P of X is true. So, how you would write that? The set, all X, element of S, such that P of X is true. This means such that. And P of X is a function or a property. So X is an element of S such that P of X is true. Say P of X is X is even. And S is equivalent to Z. X is an element of Z or S such that X is even. So in set roster notation, this would be something like that to indicate it's even integers. But that is the basics of set builder notation. The vertical bar is translated as being such that, and you'll see that a lot this semester. But the set of all X that are elements of S such that P of X is true. So now subsets. A subset is a basic relation between sets where if A is a subset of B, that's not a C, that's a tilted over U actually, means that all the elements, all the elements of A are in B. It is a subset of B if all the elements of A are in B. Now this is a symbol here. I don't know if you can get it on a computer. It's kind of challenging to find the right font and all that sort of stuff to get that symbol. But that is a subset that is either fewer elements or as equivalent to B. So in this case, A may equal B. It's kind of like the greater than or equal. So the A without the equal sign is a proper subset of B. Which means A is smaller than B. It's so you can also have A is not a subset of B, or A is not a proper subset of B. Those are acceptable symbols as well, and their meanings. And, yeah. So some examples. Let's see here. 2 element. Is that true? Is 2 an element of that set? Yeah. Going back a little bit. Now, how about this? 2 is that true? No, because 2 is a set. This set contains no sets, so it's not there. But what about that? Yeah. 2, the set of 2 is a subset because both sides of this symbol have to be a set, is a subset of 2, 1, 2, 3. What about that? Pardon my scribbling the curly braces. Yeah. The set of 2 is an element right here of this set because it's nested inside the outer set. Now, that's one way to relate elements. Another way to relate elements is using Cartesian products that you create from sets. So, given elements A and B, let's see here, Cartesian product. Given A and B, that notation denotes the ordered pair, consisting of A and B together with the specification that A is the first element and B is the second element of the pair. So, this is not equivalent. They are not the same. Yeah. That's the symbol for equivalence. That's equals. That's for numbers. Slight difference. Maybe I'm getting a little ahead of myself on using that symbol, but yeah, it's three lines is equivalence. So two ordered pairs are equivalent if A equals C and B equals D. The ordered pair A and B is equivalent to C and D if A is equal to C and B is equal to D. So that would be equivalent. Yeah. That the order matters. Yeah, so the first element is A, first element is C. So if they're equal, then the first elements are equal. Likewise, second element, if they're equal, then and if both conditions are true, then the two ordered pairs are equivalent. Now, these are kind of analogous to arrays because duplication does matter and order does matter. But in C++ at least, the ordered tuples or pairs or triples or whatever are denoted with, that's what you use to denote an array and the elements of an array in C++, right? I've never taken C++, so I'm just guessing here. No, so these are equivalent in C++. In this class, stick to the parentheses. So this indicates a set, in which case A and B could be in any order in this class. So it is a slight difference in representation between what you're used to in C++ versus mathematically speaking. Okay. Let's see here. A Cartesian product. So we're going to get to. Well, okay, let me read this so I don't get it right. Given sets A1, A2, A3, etc. to AN, the Cartesian product of A2, A1, A2, A3, A4, etc. denoted by, I'm just going to do 2 for right now, A and B. The Cartesian product, I'll write this again here. A, big X, B is a set of tuples, the number of sets being done with a Cartesian product on. So this one would be a ordered pair. The set of ordered pairs such that X is an element of A and Y is an element of B. So what does that look like? Well, let's say A is ABC and B is 1, 2. So the Cartesian product is the set of ordered pairs where X is an element of A. All the X's are elements of A, and all the Y's are elements of B. Every combination. So it would be A1, A2, B1, B2, C1, and I'm sorry, yes, yeah, that's right, C2. That would be the Cartesian product. All combinations of the ordered pairs where the first element is an element of the first set, and the second number or second element is an element of the second set. And it's all combinations. So the number of elements equals the number in A times the number in B. Now, something that might bring back some memories of analytic geometry or algebra. What would that be? Real numbers cross product with real numbers. Assuming R1 and R2 is R1 is on the x-axis and R2 is on the y-axis, you have the Cartesian plane. Remember that term from algebra? The Cartesian coordinate system? You remember that term? They didn't use that term in algebra? Really? You didn't and the alternative coordinate system is the polar coordinate system. I know polar coordinates were used in at least in calculus. I don't know if it was Cal 2 or 3, but 3. Yeah, the Cartesian is the axes at the right angles, and the polar coordinate is angle and radius. But yeah. So yeah, it is a Cartesian product that would be the x and y coordinates on the Cartesian plane. So, yeah. So we can move on to the language of relations and functions. Now, let's see a definition here. Relations and functions. All right, definition. Let A and B be sets. A relation R from A to B is a subset of a Cartesian product with B given an ordered pair X and Y in a Cartesian product with B. X is related to Y by R, written X, R, Y, if and only if X, the ordered pair X, Y, is in R. Okay, so what does that mean? Okay, well, let's say the domain is A. Is let's do this, what I just did a little bit ago. A, B, C, and the codomain is 1, 2, and the this is the Cartesian product of that. Oops. Already wrote that out. So a relation X, R, capital R, Y, let's say is the set, let's see here, we'll do the set A1, B2, C1. Basically, it's a subset of the Cartesian product that contains a relationship between X and Y. A is related to 1, B is related to 2, and C is related to 1. No other relations. A is not related to 2, B is not related to 1, and C is not related to 2. Okay? Now, you can say, let's do the example that I have written down here. Say your sets are 1, 2, and 1, 2, 3. A is 1, 2. B is 1, 2, 3. And the relation from A to B is, let's see here, let's see here, okay. R equals, let's see if I can do this in set notation, X and Y is an element of A Cartesian product with B such that X minus Y over 2 is an element of Z. Now we're getting into the thick of all the mathematical symbols and stuff like that that we're going to be using for the semester. So, let's see here. What would the elements of R be? Well, 1 minus 1 over 2 is that take your Cartesian product, 1, 1, 1, 1, 2, 1, 3, okay, and 2, 1, 2, 2, and 2, 3. That's your Cartesian product, those ordered pairs, right? Okay. Which ordered pairs satisfy this condition? Just a little bit of math. So let's say, let's do the Cartesian product. So 1, 1, 1, 2, 1, 3. And 2, 1, 2, 2, 2, 3. So that's your A Cartesian product with B. Now, what pairs satisfy that condition? 1 minus 1 over 2 is 0, so that would be true. 1 minus 2 is minus 1 over 2, which is not. Does not satisfy that condition. 1 minus 3 is negative 2 over 2, which is negative 1, which is an integer. So that would be true. 2 minus 1 over 2 would be 1/2, so that would be not in the set. And then 2 minus 2 is 0 over 2 is true. That is an integer. And 2 minus 3 is negative 1 over 2. So that would be false. So that would be out. that would be out, and that would be out. Does that make sense? Kind of, sort of? No, an integer. This is Z is for integers. Yes. No, it can't be a fraction or a decimal. Yeah. So this condition has to be true for these ordered pairs to be in the set. Again, this is the domain, and this is the codomain. Now, there's a way to represent this graphically, a relation like this, because you have two elements. We can have two areas. Let's see here. 1, 2, and 1, 2, 3. Okay. 1, 2, 1, 2, 3. Okay. Now you can draw an arrow from the domain to the codomain elements, the elements of the domain to the codomain elements, to represent that pair being in the relation. So if I'm recalling correctly, it goes like so, and like so. Is that all the three? Yeah, 2, 2, 1, 1, 2, 2, and 1, 3. Yeah. So that is an arrow diagram of a relation. So, pretty simple. This is graphically easier to see that 1 is related to 1 and 3, and 2 is related to 2. So, the arrow diagrams are handy. Now, a function is a particular type of relation, and I'm going to use this diagram to demonstrate what a function is. Let me erase this. All right. Now, a function is a relation between two sets such that every element of X in A, there is an element in B such that there's an ordered pair for each element in the domain. There's an arrow coming from each element of the domain. So this satisfies that condition. Now, the other condition is that for every element of B can only be related to there can only be one element of B related to each element of A. Which means this is not a function. Okay? So we can take that out. Now it's a function. A function, oops, all of A has arrows, has a pairing with exactly one element in B. Now there could be elements in B that are unused. That's fine too. Yeah. Yeah, it's still a relation. All functions are relations, but not all relations are functions. So you can have that would still be a function. The result would the function has both elements of A in relation to related to 1, but all elements of A have a arrow pointing to the an element, a unique element in B. Now this is kind of like a function in programming. Given the inputs, a function returns one distinct result. You can't have like the square root function. In the square root is not a true function. It is typically implemented as a positive square root. But if you look on the graph of a square root, it looks like this. For every x, there's 2 y's, except for at 0. So it's not a function. It is a relation, but it is not a function. You have to distinguish whether or not it is the positive square root or the negative square root. But let's see here. I don't think we have enough time to get into the language of graphs, but so we'll call it a day here. If I am recalling correctly, the chapters 6 and 7 go into more depth on sets and relations and sets and functions. These 2 chapters are extra credit. So if you choose, there are 4 sections in each chapter. The slides are in the files section of Canvas. If you choose to, you can go to download those slides, go through them, do the homework assignments on Canvas, and the resulting grades will be used to substitute for your lowest quiz grade or your lowest test grade. Yes. Yeah, I'll put it in an announcement. But before I did that, I wanted to cover sets and functions, so you wouldn't be completely lost going into if you wanted to start on those extra credit assignments now. But yeah, those two chapters go into sets and functions in more depth. The due dates on those are basically the end of the semester, so take your time with them. If you run across a concept that we haven't covered in class yet, you can wait. There's no big rush on those. But typically in past semesters, about half the students have done the homework, extra credit, and it has helped their grades. So, or if you just want to get more in depth into these concepts, have at it. But yeah, I'll put that in an announcement probably tomorrow. But in the meantime, have a good day. Have a good weekend. See you on Tuesday.